All right, so let's get started again here. So again, we're talking about the Gaussian primes, excuse me, the Gaussian integers, I should say. This is a blurb by Keith Conrad that I'm following. Hopefully we're going to finish it today. Let me restate that. We were going to finish it today, which means we're going to skip some proofs, all right? Or I guess I could be more, what's the word, optimistic, or put a paint a rosier picture. I'm going to sketch some proofs today. How about that? Lemma 6.5, which is where we got to. This one says that if we have pi prime, so pi is used a variable here, yeah? Prime and zi, then the Gaussian integers, alpha 1, alpha 2, alpha r. Those are just four, instead of saying I should say four Gaussian integers, alpha 1 through alpha r. If, here's the punchline, if pi divides the product of all these Gaussian integers, then what has to happen? What would you think you can say? If a prime divides a product of integers, then it has to do what? It has to divide some alpha j, right? Now, notice that doesn't say for just one j. Like, it's possible it could divide more than one, but that's the result. So the proof is on page 13. He does it for two things, all right? And then he says that if you do it for more, it's a straightforward induction. Now, so this brings us to the prime factorization, all right? So what's not true? Let's start with that. Well, let's talk about integers even. How about in z? Right? If I have a times b is equal to c times d and a, b, c, d prime, what can you say? I mean, earlier in this course, we talked about the prime factorization, right? And the uniqueness of the prime power factorization. So it seems like we should be able to say a equals either c or d, right? But we can't say that, actually, because the truth of the matter is this could be 3, this could be 5, and that's also equal to minus 3 times minus 5. The reason we didn't face that ambiguity is because we limited the discussion to positive prime factors. We looked at factorizations really just of positive numbers, truth be told. So we avoided the ambiguity by ad hoc limiting the discussion to just positive integers. So the same trouble exists in the Gaussian integers. If you have pi 1, pi 2 equal to pi 1 prime, pi 2 prime, where these are all Gaussian primes, that does not imply that they have to be equal, all right? So what's up here is that like minus 3 is minus 1 times 3, right? Minus 5 is minus 1 times 5. The thing is, what are the units in z? In z, the units are plus or minus 1, right? So what are the units in zi? Gaussian integers, you got units what? You still got the plus or minus 1, but now you also got the plus or minus I. All right? So if you have a product of primes is equal to a product of primes, right? You don't get to say that they're equal, but what you do get to say is that there exists some reordering. So they are unit multiples. So like in this example that I just made up here, you'd either have pi 1 prime is equal to u times pi 1, or you'd have pi 1 prime is equal to u times pi 2, and then you have pi 2 prime is equal to some other u, let's say, well, I don't want to say bar, let's say u2 pi 1, or pi 2 prime equals to u3 pi 1, no, 2. Yeah, so it's either, my bad, this is supposed to be pi 1. I want these to be two separate cases like this. Let me check on my enumeration. So 1 goes to 1, 2 goes to 2, or 1 goes to 2 and 2 goes to 1. That's what I should have pattern. Either they're flip-flopped or they're the same, but we have to allow for the possibility that there's a unit multiple. And that unit multiple could be plus or minus 1 or plus or minus I. So we face this ambiguity when we're looking at a prime factorization of Gaussian numbers. All right? So like just to drive that point home, here's an example which illustrates this ambiguity. 5, right? Well, 5 is 1 squared plus 2 squared, right? So we can write that as 1 plus 2i times 1 minus 2i, right? Those are both, you can prove that those are both prime. How would you prove that those are prime? Yeah, if the norm is prime, they're prime. And the norm of 1 plus or minus 2i is 5. If the norm is prime, they're prime. That's the theorem we had last time. Prime norm implies prime in the Gaussian. The converse is not true. The norm of 3 is 9, but 9 is not prime, yet 3 is prime in the Gaussian numbers. Oops. I'm solving your homework. My bad. But my point to you is we can easily create another factorization, which looks a little bit different, right? By simply multiplying by 1. How do you multiply by 1 in an interesting way here? Well, I don't know. How about we multiply this one by I and multiply this one by minus I? Because minus I squared is 1. After all, we're just multiplying by 1. So straight away, this gives us I minus 2 times minus I minus 2, right? So there is a different factorization of 5. A hideous, ugly factorization of 5, but nonetheless a factorization into product of primes. Okay, I times that one minus I times that one. So, moving along here, let me state theorem 6.6 for us. And, you know, the proof, really, when you get right down to it, the proof of lemma 6.5 and the proof of theorem 6.6, it is really much the same song and dance as it was in the integers. So I don't mind overlooking it too much. It's just that here you have to drill down into various cases and things, and it's based on like an induction on the norm. It is different, but like the overall spirit of it is much the same. And you can read it. It's on page 14 and 15 of this blurb. So here's unique factorization, and I'm just going to say what I already said, which is if you have a product, a Gaussian integer, and you've got it factored as a product of primes, let's say R of them, and then you have it another product of primes, all right, let's say S of them, all right, so here the pi's and the pi primes are prime in Zi, then punchline, then R has to be equal to S, and pi sub I prime is equal to, you know, some unit, let's say the ith unit, times pi sub j for some I. I mean, each I has to match up to some j. If you want to, you could relabel them so that 1 matches with 1, 2 matches with 2, 3 matches with 3, whatever, all right? So this is unique factorization, okay? So let's just chase this rabbit here for a minute. How to factor. How to factor in Zi. How do how do you actually find these prime factorizations? I don't know the general robust theory of it. I mean, really, Conrad just gives us some sort of small hints about how to do it. So I'll follow his lead. And so what he says is, well, let's just take a look at 3 plus 4i, see how we could factor that, all right? So what he does is he's like, all right, so we know that if this is equal to like gamma times delta, then what? Then like the norm of gamma times the norm of delta has to be equal to the norm of alpha, right? So these guys have to divide, must divide this guy, right? So what is the norm of alpha here? You got yourself a 3 squared plus a 4 squared, also known as 25. That's 5 squared, right? So that means that any non-trivial factorization of 3 plus 4i, right? I mean, at this point in the game, we don't know. It could be prime, right? Well, it has to have norm 5, right? So this tells us that we must have like norm of gamma equals to norm of delta equals to 5. So then the question is, if we have, say, gamma equal to a plus ib, and with a squared plus b squared equals to 5, what are your choices? How can you achieve that? Like there's a finite number of a plus bi which give you back 5. Yeah, 1, 2, 2, 1. Yeah, very good. So we could do, so you're like 1 plus 2i, 2 plus I, right? Very good. But we can also do minus 1 plus 2i. We can do minus 1 minus 2i. We can do minus 2 plus I. We can do minus 2 minus I, right? Is there any other choices for the magnitude of a and b other than 1 and 2? I don't think so. Like, I don't think we could use 3. You can't use 0. This is it, right? But that's not it, because units. We can multiply these guys by units, right? Multiply these plus or minus I, right? Actually, I think if we just multiply by I, that may suffice because I put minuses in. But I'm notoriously bad with combinatorics, so I wouldn't follow me if I were you. I'm just giving you a hint. Think for yourself. I minus 2, minus I minus 2, minus I, minus 2i squared is plus 2, right? So are we getting back to any of the same ones I had before? Probably. Yeah, check it out. See this? See this right here? This is this right here. So you say there's actually only 6 cases. So do I have them?
Yeah, it's 1 and 2. And
so it's just these are the 6 cases? Yeah. So actually, I was wrong. Multiplying by I just kind of goes this full circle, as we just saw. Multiplying this one by I takes me over to this one. Okay, so actually there's no more cases. It was an unfounded concern. So then what? You got 6 ways to do it. So you just try to do it. We need 3 plus 4i something times something. Both of the somethings have to be taken from that list of, hey, what's 6 choose 2? 6 choose 2.
6 choose 2, 2 and 3.
That would be the number of possibilities here, right? But anyway, so I don't know, 1 plus 2i, and then what? I got to get a 3 somehow. How do I get a 3? 1 minus 2i maybe? See, because then I get. So that's not going to work.
You need I. You need a singleton I.
I need a singleton I, but then I can't get the 3.
Yeah, you can.
How can I get 3?
Then you get the 3i. Oh wait, no.
I mean, this doesn't work because I get the 3 because I get 4. No, that's going to be 5. I'm a dummy. That doesn't work. I think that's actually 5.
Yeah, that is
Duh, that's 5. My bad. So like, don't do that. Let's try minus 2. I don't know. You tell me what to try. Let me wipe the slate here.
So we need 3, so that means we do
Just try something, I think, is the way to do it. You know, like
1
just
minus I, 2 minus I?
1 minus I. Well, the 1 minus I wasn't 1. There's always a 2. Which one? Where's the 2?
Oh, man, yeah, never mind.
Oh. How about 2 minus I and 1 plus 2I? I don't know. Right? That will at least give me the 4I. And it will give me 2. So that's 2 minus I plus 4I.
Minus 2I squared.
Which is, oh, I'm a dummy. That give me 3I anyway. That give me what? 4 plus 3I. Well,
That's minus 4.
we just figured out how to factor 4 plus 3I. There's a feather in your cap right there. Of course, these are not equal, right? The point is that this is not an equality.
Okay.
So let's try again.
2 plus I, 2 minus 2 plus I,
Minus 2 plus what?
I.
Plus I. All right, we'll try that. What do we got? We got minus 4 plus 2I minus 2I plus I squared, also known as negative 5. Hey, check it out. You just factored minus 5. Good job. Unfortunately, not equal. All right, I'm going to put us out of our misery. What we should try is 1 minus, interesting. I forgot something. What's another possibility? Do they have to be distinct? We were never going to find the answer with what we're doing, because the answer is actually a little bit surprising. Try this, 1 minus 2I squared. What does that give us? See, that's a possibility. They both have norm 5. So that gives me 1 minus 2I plus 4I squared, which gives me what? That gives me minus 3 minus 4I, right? Well, now, yeah, that's not equal either, but we see what to do. It's easy to fix, right? So 3 plus 4I is equal to minus times 1 minus 2I squared. Or if you like, you could write it this way. It is 2I minus 1 times 1 minus 2I. Actually, it should have been it is the product of two of them, isn't it? So it's that one, 2I minus 1 times 1 minus 2I. We could have got it. I was wrong. Do I have 1 minus 2I in the list, though?
Yeah, you have 1 minus 2I.
Okay. Where is it? I don't see it.
Oh, wait.
I think I'm missing it. I should have had 1 minus 2I also up here. I think I'm missing. Like I told you, do not trust me on the combinatorics. It is. All right. Anyway, I think you can see, even for a numerically relatively simple one, it is actually kind of a pain to figure out how to factor, right? Which is why you should be very grateful that I sent you the link to a website that will factor Gaussian integers. That thing is fresh. It was updated like a week ago. But to be clear, it doesn't give you a prime factorization, nor does it claim. It just says it's a factorization. So, yeah. All right, anyway. So he has another example on page 15, which is substantially worse. We're going to skip it. I mean, he admits there that he did not calculate that one by hand. Then he has a section on modular arithmetic in the Gaussian integers, which is very interesting. Among other things, he proves many of the basic results we have in number theory, like Fermat's little theorem and a few other things. And just generally the properties of modular arithmetic, they equally well can be sort of built over the Gaussian integers. However, we're going to skip that section. We may come back to it as we get deeper into ring theory and such. So now we're going to look at applications. All right, so section 8. I should have probably left that lemma 6.5 up because we'll actually use that if I actually go through a proof today. Okay, so section 8, which is applications of the Gaussian integers to arithmetic. In Z. All right. So basically, just to put the first thing front and center, most of how this is all going, it all comes back to the simple formula that a squared plus b squared is a plus ib times a minus b. That is the central motivating theme of this section, right? And it seems like kind of a small thing, but it's actually not. And so what we're going to see is this list of claims. We're going to see that a prime number is a sum of two squares in just one way. We're going to see a classification of primitive Pythagorean triples. We're going to see a classification of primitive solutions to a squared plus b squared equals to c cubed. We're going to see the only integer solution to y squared equals to x cubed minus 1 is 1, 0. This is an old result in number theory. And then we're also going to see a systematic way of finding integers, which are sums of squares in more than one way. So let me just get right into it here. Theorem 8.1. All right, enough of this. There we go. So we'll use that one again. It's dry. Here is the theorem. If prime number p is sum of squares, then it is so in essentially one way. What does he mean by that? So he means that p equals to a squared plus b squared where a and b are unique up to ordering in signs. All right. So let me just make it a little less mysterious. This uniqueness he's claiming. Like, let's just look at 5 for a second. So 5 is equal to what? It's equal to 1 squared plus 2 squared, right? It's also equal to 2 squared plus 1 squared. It's also equal to minus 1 squared plus minus 2 squared, right? It's also equal to minus 2 squared plus minus 1 squared. But that's it. So that's what he means by essentially one way. All right? You see what he means? Does that make sense? By essentially one way? Essentially is given meaning by the sentence which follows. So. All right, so let's see if we can prove this thing. All right, so proof. He's like, let p equals to a squared plus b squared, all right, for a, b, p, and z, p prime, right? Then p is equal to a plus ib times a minus ib in the Gaussian integers, right? So P is not prime in the Gaussian integers, it's composite, as you can see. All right? And since, ooh, hey, very nice. Since the norm of P is equal to P squared, and that's equal to the norm of A plus IB times the norm of A minus IB, right? What does that tell you about the norm of A plus or minus IB? They're equal to the same, and they're equal to P because P is a prime. So by the prime factorization, the unambiguous one in the positive integers we used at the start of this course, there you go. The norm of A plus or minus IB is P. What does that say? Thus, well, A plus or minus IB is prime, yeah? I don't know if that actually matters, but I just can't help but write it. This may actually have nothing to do with the proof, I'm just saying. Okay? Well, he says that too, I guess it matters. So if there is a second representation, right? So suppose you have a second representation of this prime P, right? In terms of, say, C squared plus D squared. What's that going to say? What would we like to show? If P is equal to C squared plus D squared, right, which is C plus ID times C minus ID, right? Then what's that mean? So you've got this is equal to that, right? And by the way, by the same argument we just gave, C plus ID and C minus ID are prime, right? So we have factored P as a product of Gaussian primes in two different ways, right? What are the possibilities then? Yeah, so we either have, like, well, they don't have to be equal, right? They have to be up to a unit multiple. So we could have A plus IB equal to a unit times C plus ID, right? And A minus IB equal to some other, let's see, unit 1, unit 2 times C minus ID, right? Or, other possibility, you could have A plus IB equal to U3, let's say, times C minus ID, and you could have A minus IB equal to U4 times C plus ID, right? These are the two sort of generic cases possible here by the unique factorization of Gaussian primes, right? What it is? Okay. Now, think about it. U1, U2, U3, U4, what are these? Yeah, they're equal to plus or minus 1 or plus or minus I, right? So, like, we can just kind of go through it and think about, you know, how this works. I'll just do a sample calculation. So, like, if it was I, if U1 was I, right? So I'm looking at this case right here. Suppose that U1 is I. What happens? Well, you get IC minus D, right? So in this case, we see that A is equal to minus D and B is equal to C, right? So as you can see, the other version, the other breaking of the prime down into a sum of squares, it's the same numbers up to a reordering in this case and multiplication by minus 1. And you can sort through every last one of these possibilities. It always works out this way. If you multiply by, if it's plus or minus 1, then like A matches C and B matches D for this one, right? And if it's I, then it flips the C and D and the A and B. But it's always either plus or minus 1 times one or the other one. So it's exactly what the theorem claims. I hope I've shown you enough that it's believable, right? To actually write all those cases out would not be interesting. I think he has a slicker way to get around this in the blurb. Well, No, maybe he just goes through the cases. I don't know. Okay, so anyway, I think that proof is worth our time because it's not just an induction, which kind of, I don't know. There's a lot of proofs by induction here, which are, testament to the power of induction, but they kind of leave me with not much more intuition about the subject. So I'm like, yeah, whatever. Maybe I just don't know enough number theory to appreciate the inductive proofs just yet. But actually, the same is true for linear algebra. There's a lot of things you can prove with induction. After I give the inductive proof, I don't really feel like I've gained anything except a proof. If I can give a constructive proof, on the other hand, of that thing, maybe I've gained a method of calculation. But anyway, maybe I'm just a constructivist. So example 8.2, I'll go through this here. So he says the fifth Fermat number. All right, so what is that? It is this. It is 2 to the 2 to the fifth. All right, so plus 1. And that happens to be equal to 429, 496, 7297. I mean, obviously, right? And so that's the fifth Fermat number, and he says that, well, that's easily the sum of two primes because that is 2 to the 16th. How do you get that? Oh, 2 to the 16th squared. I'm a dummy. 32 is 16 times 2, right? So 2 to the 16th squared plus 1 squared, right? Now, I've not proved that it cannot be written as the sum of another two primes, right? But it can be. You can prove that, in fact, this is prime. This is actually prime. I don't know if I've proved it. I don't think I have, but you can. In contrast, 2 to the 6th, well, that plus 1 squared, well, plus 1, that's the 6th Fermat number, right? And so, of course, you can do the same trick we did there. So 2 to the 6th is 64, so you can do like 2 to the 32 squared, right? Plus 1 squared. So that's one way to write the 6th Fermat number as a sum of squares, right? But, you know who? Euler. What did he do? Well, Euler said, yeah, well, obviously you could also do 62,264 squared plus 20,449 squared, right? I mean, come on. And see, so if you also could see that, and you'd also proved Theorem 8.1, what does it mean? Theorem 8.1 says what? So Theorem 8.1 says that, 2 to the 6 plus 1 is not prime, because it can be written as a sum of squares in two different ways. And indeed, Euler found that this is actually equal to, 641 times 6,700,417. So he must have had to buy a lot of batteries for his calculator, huh? I mean, that's not accurate, right? They didn't have calculators. Like, what they had was time, though, and a lack of the internet. But well, anyway, Euler's a special person. So next up, we want to study solutions to a squared plus b squared equals to c squared, where a, b, c have no common factor. All right. And so then there's said to be a primitive Pythagorean triple. All right. So let me just go ahead and state the theorem here. And we've seen this before, all right? But actually a proof is given here. We just claimed it before, we didn't really prove it. Theorem, every primitive Pythagorean triple ABC with A odd. So he argues that at least one of A or B has to be odd in the page before. So it's not, this is not a limiting, that's like a necessary, it's just for the sake of labeling, all right? You can assume one of them is odd. Either A or B has to be odd. So why not say A is odd? Then A is equal to m squared minus n squared. B is equal to 2mn. And C is equal to m squared plus n squared, where m and n are greater than 0. Oh, excuse me, I've stated that imprecisely. M is greater than n is greater than 0, and they're relatively prime. All right, with m not congruent to n mod 2. And he says, conversely, for any such choice of m and n, the above formula is a Pythagorean triple. Different choices of m and n give different primitive triples. All right? So that's, that's a pretty neat result. What do you think the proof to this looks like? Well, the conversely part you can just derive. That was a homework problem for you guys. I said if A was this, B was this, C was this, then show that A squared plus B squared equal to C squared. I might have used X, Y, and Z in your homework, but yeah, you proved the converse direction in homework, absolutely. But the fact that every Pythagorean triple has this form, that's not something we proved before. That's different, right? So, and so basically the argument goes something like this. If we have A squared plus B squared equals to C squared, right? Where A is odd, B is even, C is odd, then this factors into A plus IB times A minus IB equal to C squared. All right? And he argues, you can argue, that A plus or minus IB are relatively prime. More than that, you can argue that A plus IB and A minus B have to be primes here. Gaussian primes. I think that's the case. I may just say, let me yeah, I shouldn't say prime. They have to be relatively prime, all right? So A plus has to be relatively prime. Oh, that's what I said. Now what? So that's shown on page 26, all right? So let's think about what we have. So what do we have here? We have the product of two relatively prime things, right, is equal to a square. Yes. See that? The product of two relatively prime things is equal to a square. What does that say about the prime factorization of either A plus IB or A minus IB? Could I have something like, and I know this is just factually inaccurate, but could I have something like this? Like I can't have something like that. I have to, if I've got let me not say 5. Let me say I've got like, 10 squared, right? If I have 10 squared there, well, the fact of the matter is that 10 is 2 times 5 squared, right? It's 2 squared times 5 squared. See, so if you've got a square on one side and you've got a relatively prime, right? They don't have to both be primes. It's just easy for my example. They're both primes. I mean, you could have, 10 times, you could have like 100 times 9, and that would be 900, right? So 900 is 30 squared, right? And that's equal to 10 squared times 3 squared, right? So these guys don't have to be prime, but they have to be relatively prime. But the point is, because of the unique factorization theorem, this says that a plus ib has to be equal to like a unit times, m plus in squared. But then what he argues is we don't have to put a unit there, because if you think through it, what are your choices? Your choices are 1, right? You could be 1. You could be, what if you use minus 1? Minus 1 is what? Minus 1 is equal to like I squared, right? So if you had the unit was minus 1, you could factor the I inside, relabel m and n, you'd still have actually a perfect square, right? So if the unit is 1, if the unit is minus 1, we can bring the square inside. We can just write it as a square. I think if it's, what about I? Can we bring the I outside? If the unit was I guess we might be stuck there. So he gives some arguments here on page 27 where he explains that, in fact, that can't be a consideration, and ultimately he argues that, in fact, so I'm setting aside some of the little details here, but basically he argues, well, actually, this has to be equal to m plus in squared. All right? So the specific arguments to rule out that case of unit equal to I are given on page 27. But anyway, long story short, you can argue that this a plus ib has to be that. But once you know that a plus ib is equal to m plus in squared for some m and n, what does that give you? M squared minus n squared plus 2imn, which shows you a is equal to m squared minus n squared, and b is equal to 2mn. And then you can, as an easy exercise of algebra, you can check that a squared plus b squared is equal to, m squared minus n squared squared plus 2mn. And this is your homework problem, actually. And that works out to m squared plus n squared when you do it. And that's the theorem. So there are many details I've left out, right? Like there's a lot of different cases to pin down and throw out. I'm suppressing that part of his blurb. He has all of the gory details on page 27, but that's the heart of it, what we just did. Theorem 8.4. I'll try to be quicker with this one. This is really not, I want to make sure we have time for the later theorems. So if you have a squared plus b squared equals to c cubed, with a and b relatively prime, then he says that you can prove that a and b are given by particular formulas. So I'm just going to whitewash the details, so to speak, here, just cover them up, and just get straight to the heart of the matter. So the idea, basically, of the proof is to go, so a plus ib times a minus ib is c cubed, right? Then you argue that because it's a cube, and it's easier for the cube because all of the units are cubes. 1 is equal to 1 cubed. Minus 1 is equal to minus 1 cubed. I is equal to something cubed, what it is. What's I equal to the cube of what? Minus I cubed. believe you got it, because that's,
Yeah, -1 times minus I.
yeah. So that's that. And then, of course, minus 1, wait a minute, I already got that. Minus I is just I cubed, right? So the point is, if you have a plus ib equal to a unit times a cube of I plus m plus in, then that unit cubed, right? That unit is the cube of something. So you can just pull that inside and relabel mn. All right. Now, the argument again is basically that these guys can be argued to be relatively prime because they're equal to the cube over here. By the theory of unique factorization, it forces a plus ib to be a unit times a cube, right? And then we can argue that because that cube can be pulled in, it suffices, right, to just look at a plus ib equal to m plus in cubed. So you cube that thing, what happens? What's m plus in cubed? It is m cubed minus 3mn squared plus I times 3m squared n minus n cubed. Skipping a little algebra here. And the point is, there's your formula for A, there's your formula for B. And of course, if you, let's see here, and you can calculate that a squared plus b squared, this I'm not going to do it, but you can check a squared plus b squared actually works out to m plus n cubed. So m squared plus n squared. I still got it wrong. No, I don't. M squared plus n squared cubed. So the c basically is m squared plus n squared. That was in the theorem. I haven't written the theorem. I mean, theorem 8.4 says a is equal to this, b is equal to that, c is equal to that. Those satisfy a squared plus b squared equal to c cubed. But this is, I mean, this is just such a brilliant idea. The idea that to take the sum of squares and break it down to a product of these, Gaussian integers. It's really interesting. So the hole in their thinking in the time of Euler is they hadn't proved the unique factorization. All right? And so they were working on this assumption that unique factorization still works in these number systems. So what we'll see next class is it's not always the case. As you go on to further examples past the Gaussian integers, we lose unique factorization. So they were building their house on sand, so to speak. And this is what, Gauss was aware of this, and this is why Gauss didn't use these methods in his disquisition Arithmetica, or whatever, the big book he wrote when he was 19 in 1801. All congruence arguments, technical congruence arguments, as a way around these kinds of arguments, because he didn't trust them. Because, well, they're not trustable until you prove some things. Yeah. Yeah. Don't spend too much time studying Gauss if you want to feel good about your mathematical accomplishments. Unless you're one of about 10 people in the world. He didn't have a cell phone. Listen, guys, I'm going to skip this one. I'll just write it. But Theorem 8.5, it's that if you want to look at y squared equals to x cubed minus 1, only has solution xy equal to 1, 0. That's the only solution. Integer solution, right? And so let me just kind of tell you the method of, what do you think the method of the proof is? Right, you rewrite it as x cubed is 1 squared plus y squared. You factor that, y plus I times y minus I. Then you argue that these have to be, that y plus or minus I are relatively prime. Then you argue that they have to be a cube. And then you look at the possible ways that you could have, But anyway, then it produces a contradiction somewhere in this story. Again, that's on page 29. So, but it's really the same trick on all three of these theorems. Oh, fun fact: Lebesgue showed that y squared equals x to the d minus 1 has no solution for all d greater than or equal to 2, except, well, d equals 3, right? D equals non-zero. He's demanding non-zero x and y. So this doesn't count. This is 0 for y, so it wouldn't mess with remark 8.6. So let us talk about how to do your homework problem. Eh? We should do that, shouldn't we? So guys, how is it that some numbers are written as sums of primes in more than one way? Well, here's how it happens. So we've got like 5 is equal to 1 plus 2i, right? Times 1 minus 2i. And 13 is 2 plus 3i times 2 minus 3i, right? So that means 65 is, well, what is it? It's 1 plus 2i times 2 plus 3i, right? Times what? 1 minus 2i times, what is it? 2 minus 3i, right? So what's this give you? I've got like 2 minus 6, right?
2 minus 6.
7. I got, or did I do it wrong? 8. Oh, it's not 7, is it? 4 plus 3, right? 7i. So that's that one. What's the other one? 2.
6, 2, and 3, and 4.
So I think it's minus 4. And then we've got minus 2i, minus 3, so minus 5i, yeah? So rewriting this just a bit, this is minus 4 minus 7i. And over here you have minus, well, I just write it minus 4 minus 5i, fine. It doesn't really matter. You don't have to pull the minus out if you don't want to. So take the norm, and see this, I'm still doing this wrong. Curses. Oh no, I did. Well, he says 7i plus 7i. I was supposed to get minus 4 minus 7i there. Yeah. Yeah, I should have got a 7 there, minus 7i, because it gives me 4 and minus 3. I neglected a 2, so that's minus 7i as well.
Minus 4, minus 7i. Yeah, that's what I got. Wait. Oh, I just pulled the negative inside, yeah.
So if you take the norm of this, what does it give you? It gives you 65 squared, right? Is equal to what?
Well, we can break the norm up, right? So we get 16 and 49, and plus 16 and 49, or no, yeah, times 16 and 49.
So 6.
165 times 65. Yeah.
Oh, I'm an idiot. Look, so dummy. I'm sorry, guys. I'm just having arithmetic stupidity at the moment.
I got minus 4 plus 7i
minus, so you get minus 4
Yeah,
plus 7i.
yeah, and then that's right, yeah.
Okay, so what does this give you? This gives you 16, right? And then minus 28 plus 28, those cancel, so plus 49. All right? But on the other hand, you can look at 65 as 64 squared plus 1 squared, right?
Yeah.
Which, of course, we easily see is 1 plus 8i, coming from the 1 plus 8i, 1 minus 8i, right? It's coming from that. But the point is that 65 squared is equal to 4 squared plus 7 squared, but it's also equal to 1 squared plus 64 squared.
Squared is equal to 64 squared plus 1.
Did I do something wrong? It's not 65 squared. I should have 65. See, I'm sorry. My ability to communicate anything at the moment is waning.
Okay, so 65.
It's supposed to be 8 squared. I'm a dummy.
Okay.
Sorry. No, not fine.
65 is equal to 64 plus 1.
This up here should just be, let me just say, that's a form of 65 isn't there, and I should just have 65 equal to 64 plus 1,
And then, yeah.
which more to the point is 8 squared plus 1, so you get that factorization, you know. But I guess more to the point, maybe so this is another, I mean, this is a factorization of 65, and I think you can prove 1 plus or minus 8i are relatively prime, right? So you're taking, and these, by the way, are prime factors, right? These are prime factors because they have norms which are prime, either 5 or 13. So the bottom line is by shuffling the factors around and multiplying them out, you get different sums of squares. So essentially, if you want to build a number which can be written as a sum of squares in more than one way, you just build it from a product of primes and just shuffle the factors around. Now, here's a hint for your homework. Don't reinvent the wheel. On page 30, he gives you a number that's a product of squares in 3 different ways. I asked you to find one that's in 4 different ways. If I were you, I would just add a 4th factor and build off what he already has calculated here. That would be the easy way to do it. But anyway, sorry I spent so long on that. Probably don't have time to do what I need to do now. Oh, curses. All right. So, finally, the main event. I have 10 minutes left. So lemma 9.1 says if P is prime in Zi, then for some P in the positive integers, which is my notation for n, is his notation for my n, then we have pi divides P. Curses. All right, well, here it is. He says, it's always the case that pi divides some positive integer, namely its norm. So notice